Today we're going to be looking at the VICI VC99. A few people had asked me about running this meter. The meter was shipped inside of this bag. First thing that I noticed were these shipping labels. It appears ... would be compared, fluke. Compared, fluke. I'm assuming they're trying to market this as somehow being comparable with a fluke meter. Comes with a nice little pouch. Looks like the operator's manual's on English. Leads feel pretty good. Little thermocouple. Case is nice and tacky. It's got a good feel to it. The knob feels pretty tight. There's one self-tapping screw that gets removed off the base. Slide this out and you can see the leads are very short. And it takes a couple of AAAs. Meter was not supplied with the batteries. That's the main reason I didn't want to run this meter earlier. You can see it says Cat 2 1000 volt rated. So this meter would be tested with a 12 ohm source impedance. I think what I'm going to do is just go ahead and take this thing apart. As long as I got the cover off. Nice shield off the backside. See that big solder ball there? Look at that, it's just hanging right on the lead. Right there, I just broke it off. Pretty poor soldering. Here's another big blob. Hopefully you can see that, it's like right here. Wow, look at this. Glass fuses. Look at how close the shunt is here. So this is the amps, milliamps, and common. So that side of the fuse is actually the milliamps. So if I applied a transient between the milliamp connector, that's going to go straight from this fuse. Wow, I mean that is tight. Right over to this shunt. Right to the ground. Well, that's scary looking. All analog trim pots. So this is the main input. See the trace coming up. It goes to a couple of PTCs up to the rotary switch. Looks like they've made a high voltage resistor out of 1206s. Well, I don't see any other protection on this meter at all. But boy, these glass fuses, that's just really bad. You can just see how close some of this is. And look at this. So this is the 20 amp current feed. Goes into this fuse. This is the other side of the fuse. So that trace runs right next to the other side of the fuse. You see how close these traces are. And then into the shunt and into ground. I mean, even if that fuse wasn't there, this is going to break down. Tell you, it sucks with some of these meters having those fuses on the back side where you got to pull the circuit board out. That's just really bad. Some of the fluke meters are like that. It's amazing, you spend $400 on a fluke meter and then you have to pull the circuit board out to get to the fuses. So I guess in that regard, this is similar to a fluke, having to yank the circuit board out. Banana jacks are not split, they are soldered straight into the board. Looks like they've done a fair job at least. Alright. Appears to power up just fine. There's no backlight on this thing. So the first thing we're going to do is a basic functional test. Okay, we'll just connect it up to our 5 volt reference here. Close enough. AC volts, it should be roughly 5. Good enough. 0.5 ohms. Good enough. There's an ohm. looks good. 50 ohms, 100, 1K. Let's try it 100. Looks fine. 10 meg. Let's try it with 100 meg. Nope, can't do it. Tell you, after buying that Bryman, I'm measuring 400 megs with that thing typically, no problem. That's a nice setup if you need to measure high value resistors. Here's a single diode, 2, yep, 3 diodes, looks good. So 1 nanofarad cap. That's pretty impressive. This is a 100 picofarad. Thought for sure to be able to pick that up. This is 4.72. Looks pretty good. Yeah, I don't know why I can't read down into the picofarad range. This would be a 0.1 microfarad. Looks good. This would be 1 microfarad. Looks good. And this is 10 microfarad. And I won't be doing anything with the 2 separate connectors here or with the current. So let's get some meters out to compare with this. On the left I have 5KY's Fluke 107. This meter cost $108. It's 6,000 counts. It's not RMS. Has a current input. To the right of that is the Fluke 17B Plus. This is a 4,000 count meter. It is not RMS. These two do not have bar graphs. To the right of the 17B Plus we have the Fluke 115. This is a true RMS meter. Cost on this is $132 versus $156 for the 17B Plus. This is a 4,000 count meter. Thing that's really missing is the temperature input. Fluke 17B Plus does have temperature. Of course we have the VICI, the Bryman BM869S to the right of that. When we test the bar graph, we'll be looking at the Amprobe AM530, and also have the original Fluke 101 here. So the 101 costing $48, 5KY's AM530 costing $80. This is a 4,000 count meter. So currently all the meters are connected to a 10 volt Fluke reference. See, the meter is fairly accurate. Tried at 1 volt. This would be 1 millivolt. Again, the Fluke 107 does not have a millivolt range. It has a AC millivolts range, but not a DC millivolts. Selecting the millivolt range for the Bryman and the Fluke 115 and the 17B Plus. Of course, if we wanted to look at the Amprobe, again, this Amprobe AM530 doesn't have a millivolt range, but it has no problems reading the millivolt. Here we're looking at roughly a 50 volt DC signal. See, the VICI is now about 100 millivolts low. The 17B Plus about 300 millivolts low. Just looking with a 2 volt sine wave applied. You can see it's running at roughly 60 Hertz. Again, this is not an RMS meter, nor is the 17B Plus. Just looking again at the frequency of all 5 meters, and we can see they're all reading roughly 60 Hertz. There's 100 Hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz. See, we're at the upper limit of the 115. It's at 1 megahertz. You can see the 115 obviously out, and the Fluke 17B Plus is out. We can see our Bryman's out of it now. This is at 10 megahertz. We are at 15 megahertz. Again, the amp probe and the VICI both still reading. Looks like the meter is good for right around 30 megahertz. This is 30.7, 30.8. And we can see they're all set to duty cycle. The Fluke 115 actually can't measure duty cycle, it can measure frequency only. So we can see we're putting out 1000 hertz right now. And all meters are reading roughly 50% duty cycle. The Fluke 107 is the oddball. 60% duty cycle. Here's at 80. It's at 20%. It's interesting to see the discrepancy. So 23.1, 23.2, 19.8, 19.8. Just to show you, it has nothing to do with the cabling. Let's swap those two around. See the same thing, 19.8, 23.2. Looking at the manual for this VICI, they actually claim this thing is capable of reading up to 60 megahertz. Obviously we weren't able to get up that high. I don't know if we were to input a higher voltage. That RF generator will put out about 3 volts. And that apparently is not enough to drive it if it is a drive problem. I have a limited number of meters that actually have a bar graph. So I've got the Bryman BM869 on the right with the VICI, and then the Fluke 115, and then 5KY's Amprobe AM530. The Amprobe AM530 can read plus or minus 4 volts. The 115 will read plus or minus 6. The VICI is plus or minus 6. And the Bryman is plus or minus 5. So I programmed the ARB to put out a 8 volt peak to peak triangle wave. So the amp probe will be full scale on the bar graph. You can see the 115 is about in here. The VICI will read up at 4. And the Bryman will read up to about 4. Let's go ahead and we'll increase the speed. Let's see how well these bar graphs track. And this is 1 hertz. This is at 2 hertz. See, the Bryman is still using basically the full scale. The VICI again would be reading roughly to about my finger here. This with a 3 hertz signal. Here we are at 4 hertz. See, the VICI is now reading between maybe 1 and 2. Bryman is still reading all the way up to 4. So with 5 hertz, again the Bryman still reading full scale. This is with 10 hertz applied. So definitely this Bryman, for whatever reason, they've got that bar graph very fast. Personally, if I've got that bar graph feature on a meter, I'd like it to be as fast as this Bryman is. All 4 meters are currently connected to my Fluke source. It's programmed for 1 millivolt. It's a little sensitive in here. I'll try adjusting this a little bit. Maybe we can get a better sweet spot. This is at 235. So yeah, the VICI appears to be a little bit more sensitive to the RF than the flukes and the Bryman. This next test, we're going to be inputting a DC high voltage signal into this VICI. For this test, I'm going to use all four of these meters. So I've got the Fluke 107, the 17B Plus, the 115, the VICI, and the Bryman. See, a little warning light came on the 17B Plus, putting out about 53 volts. Again, the 115 and the Bryman tracking very close, both reading roughly 512.3. All fairly close. You can see both the 105 and the 107, they're at the end of their limits. Okay, I've gone ahead and replaced the two flukes with the 2 amp probes. I believe those will actually read up a little higher. So let's see if we can get it up a little higher now. It's roughly 770 volts. See, the VICI is reading very close to the Bryman. Looks like the amp probe 530 is starting to beep at us. That's the limit of our power supply right there. As we can see here, I've got the high voltage probe attached and the oscilloscope sitting up behind. So currently I'm outputting a square wave. We'll just take this up to roughly 60 Hertz. And we can see the ground level is roughly at the center point. With our high voltage probe connected, you can see the oscilloscope is reading 50 millivolts per division. That equates to 500 volts per division. So roughly 1,000 volts. So we're switching between ground and 1,000 volts. Unfortunately, the only RMS meter that's in the group here is the Bryman. You can see the 3 meters are reading roughly the same value. This is all on AC, and you can see the Bryman is reading roughly 60 Hertz in the upper right. So now what I'm going to do is bias this waveform down below ground. You can see I can swing it all the way below ground or all the way above ground. Really doesn't matter. And what I'm going to do while I'm doing that is we'll be watching the meter completely below ground. This is with switching between a minus 1,000 volts and ground. You can see here. And now I'm going to increase that to 1,000 volts above ground. So we can see here. And there's absolutely no difference in the values that I'm reading. This is plus or minus 500 volts here, roughly in the center point. Still reading the same value. You can see if I select the crest mode, it's minus 571 and plus 577. So it's not quite around the 0 point, but fairly close. Next thing we're going to do is the continuity test. Thought before we get started, let's just compare the sound of the beeper. You can hear that 17B is quite a bit louder. The 107. And again the VICI. It's probably about as loud as the 107. You can just see how slow this is. Wow, it's extremely slow. And the first thing we're going to do is look at the open circuit voltage. And again, I'm just going to be using my bench meter to do this. Next, I'm going to look at the short circuit current. Next, we want to measure the open circuit resistance. And let's go ahead and measure the short. Looks like it's got quite a bit of noise on it. Looking for where it actually stops clicking. And this will be a 50% duty cycle, and we're going to measure the maximum frequency. So this is with a 2 Hertz waveform applied, and we're going to find the minimum pulse width that it can detect. Alright, for this next test we're going to be using our PTO Grill igniter. We're going to be applying a transient, both positive and negative, to the 2 inputs in all the different modes. 5 transients each, and then we'll go back and retest it. Really? Again, we're only going to be looking at the modes that are relative to these 2 inputs. Alright, let's do a basic checkout and we'll see if it still functions. Let's be looking at roughly 5 volts. Really? Shit. Totally dead. Yep. So nothing attached to the meter. It's reading 0 ohms. This will be a 1 microfarad capacitor. Let's try with a 10 mic. So the capacitance mode works. Let's just turn on our generator. So I'm putting out 270 volts right now. Doesn't appear to be able to read frequency. AC volts is out, DC volts is out, the diode resistance continuity test don't work, and the frequency input does not work. The only thing that does work apparently is the capacitance check. It smells like Unity all over. I don't see any problems down in this area. All the diodes and transistors check out just fine. I suspect if I remove the LCD here, we are not going to find any other additional protection. One thing I noticed, look at like this screw right here. See how close that is to that trace. It's like almost right over the top of it. You tighten this down enough, it's almost like it could almost cut through that trace. This path here is essentially the ground. See, would be grounding that pin right there. It's a pretty bad layout. So the rest of the devices up in this area all appear to be fine. Okay, so unfortunately there's nothing else I can do with this meter. It appears to be permanently damaged, and it looks like the main control IC is out. So So what I'm going to do is select this to AC line voltage. We're going to program up the generator for 5,000 volts. Oh, something broke down. Ooh, getting worse. Yeah, I think what we're going to do, let's turn on our half cycle line simulator here. You can see the meter breaking down. It'll definitely do some damage hitting it with this secondary generator. It's pretty impressive that the meter is actually staying functional somewhat. Okay, this will be a single transient with the half cycle line simulator. We're going to put about 600 joules into this meter. We'll leave the meter in the AC volts mode. Alright, let's have a look, see what kind of damage we got. Let's see where the blast was off to the side. Quite a bit of splatter on this back shield. See up along the edge here where it's burned. There's a lot of burn in this area here. You can see the discoloration of the banana connector. See the nice red versus the blackened area here. Oh yeah. Let's take a look at our switch. It's not too bad really. See the trace right here where it's burned through. Little burn along this area here. Up in this area here. Start of the video I'd mentioned about the clearances in this area here. We're just going to try that test. So again, this would be the milliamp range. Goes to this side of the fuse, to this side. And I'm suspecting that it's going to arc right between these two connection points here. I don't want to create a huge mess, so I'm just going to get rid of these two glass fuses. These stupid things don't belong in a meter in the first place. It's roughly 1,000 volts. That's not enough to break it down. So I'll go ahead and increase that. It looks pretty good. You can definitely see it breaking down in that area. A little difficult to tell with this camera, but it's definitely etched the back side of the fuse holder. If we had had a fuse in there, that actually would have reduced the clearances. I'm not so sure that that wouldn't have been a lot worse. Let's try it with the 20 amp circuit as well. So again, I suspect it's going to break down right here. Again, it basically goes through the shunt and back to ground. So I think what we're going to do is put the unit in this direction. We'll try to get a good shot of this area here. Again, this will be about 600 joules, 1 pulse. See the solder here just vaporized in this area. Whew. Yeah, definitely not a lot of clearance right there. Not something you'd want in your hand, that's for sure. Imagine putting a 10,000-20,000 joules into this thing, what would happen? For this test I've reinstalled the fuse. We're going to close our door because that fuse is probably going to come apart. Again, this will be roughly 600 joules. Actually spread apart the fuse holder. Looks like it tore it away from the circuit board quite a bit. Yeah, this is why you don't put glass fuses in your meters. Just looking at the data we collected for the VICI VC99. This is looking at the continuity test. Using a 50% waveform, the maximum frequency that it could detect was roughly 3.2 Hertz. Not the slowest. You can see the Unity 139C and the Fluke 115 are both in that ballpark. Again, this Amprobe AM510 to me at 8 Hertz, that's about the minimum I'd want. You can see the detection time is 145 milliseconds. So this is a 2 Hertz waveform, and I'm adjusting the minimum pulse width before the meter reliably detects it. You can see it's on par with about the Amprobe AM530, which is an extremely slow meter as well. The short circuit resistance is roughly 21 ohms, and the open is roughly 30 ohms, so about a 10 ohm hysteresis. We can see that resistance is on par with the Keysight. Open circuit voltage, 0.63 volts. On par with a lot of meters, and the shorted current is roughly 251 microamps. Again, on par with a lot of the other meters. For the transient testing, well, I was able to run the high voltage DC test, and again I took that meter all the way to 1000 volts. It didn't have any problems with that. It was damaged during the ESD testing. The only meter so far that have failed that test was the X-Tech 530, the Unity 61E, and the Unity 61D. So unfortunately I wasn't able to do any further testing with the meter, but I suspect with the design of the meter it wasn't going to go very far. Again, if we look at the original labeling that came with this meter, it said something about compare Fluke. So you can see the color very close to the Flukes. It's hard to tell the two apart. It's got a little bit orangey tint to it, but you know, it's very close. Trying to market this though as a Fluke replacement. Yeah, I don't see it. Looking at the lower cost Flukes that I've tested here, these are all actually very robust. This Fluke 101 again is yet to be damaged. I've ran this meter all the way up to 13,000 volts. Same thing with the Fluke 115, and the Fluke 107 was damaged at 15,000 volts. And the Fluke 17B Plus failing at roughly 10,000 volts. You know, these are very robust meters, all handling ESD, no problem at all. I have no concerns about the current inputs on these, except for the Fluke 101, which doesn't have a fuse. The rest of these Flukes are fused properly. They have proper clearances. So again, testing the fuse inputs, I don't really see a problem with that. I've actually done that with 5KY's 107. So is this a Fluke replacement? No, it's definitely not. I think trying to sell this as a Fluke replacement, I don't agree with that. I think you're going to get what you pay for a low-end meter for $30. Maybe it's worth it. I just wouldn't use it on anything with high energy. Yeah, hope you found the video enjoyable. Till next meter.